All right. Good afternoon, everyone. It is 2 o'clock, so we are going to go ahead and get started. Welcome. This webinar is entitled "Where is the Water Coming From? Solving I&I with Flow Monitoring." Mike Ping will be hosting it. He is the Duke's National Technical Manager. He's a graduate from Clemson University in electrical engineering. He's a licensed engineer in North Carolina and South Carolina with over 25 years of industry experience. He is married with 5 children, the oldest being 17. So if at the end of the webinar, we will ask questions, but if you have questions throughout the webinar, feel free to put them in the Q&A box. And at the end, we can take questions and I can unmute you. Just be sure to raise your hand. All right, take it away, Mike.
All right. Can you hear me okay, Caitlin?
Yes.
All right. Very good. Well, thank you everyone for joining. Again, I'm Mike Ping, and this should be about 30 minutes. So I'm going to try to reel through this very quickly. I know people are busy and your cell phones are out, so I'll try to really keep this on point. So yeah, this is about flow monitoring, open channel flow monitoring, and let's just dive right in. Yeah, so I just want to put this out there at the beginning. Quite often we have, people want to ask questions like afterwards. So if you want to go ahead and jot this down, and I'll put it up at the end as well. But if you're kind of apprehensive about asking questions at the end and so forth, that's my email, that's my cell phone. You could even text, and we could set up a call. I'm happy to support in this kind of domain at any time. That's kind of the part of the job that I really enjoy. So feel free to reach out. So topics will be why measure flow, how does it work, what it looks like in the field, a typical flow monitoring project workflow. Then we'll touch on the differences and kind of pros and cons of a utility doing this on their own versus a full-time service provider, somebody like us. We'll dive into some flow data and some examples, and then kind of an example like bigger project approach. So what flow is being measured? Just to be very clear here, we are talking about the flow of sanitary sewer. Now, sometimes this equipment gets used for other purposes, stormwater sometimes, or in industrial applications, one-off. But the equipment here that we're talking about is designed and intended to be used in the sanitary sewer system. So you can see this photo on the left here, typical sewer, and kind of the diagram over there of a manhole on the right. So why measure the flow? What are some kind of the basic reasons here? One being, and this is probably the biggest, would be to determine areas that contribute undesirable I&I. I&I meaning inflow and infiltration. So those top pictures are good examples of what that could look like. Where the top left photo, groundwater seeping in, kind of some kind of crack or a joint in a pipe segment. And then the top right picture, obviously very pressurized groundwater making its way in. And, the reason that that's not good, right, is the wastewater treatment plant in the bottom right. It's a biological process, and, ideally those see nice steady flows. It's a very expensive process. It's a big capital investment. So it's good to have those designed to have the ideal capacity, and not to be treating 5x and 10x when a rain event happens. So I&I is inflow and infiltration. Another common application will be for billing, where one utility, we'll call it Town A, has a sanitary sewer system, but no WWTP or wastewater treatment plant. And, the adjacent town that receives the wastewater, again, big investment. They need to receive some sort of funding for that. And quite often there's billing sites, and every arrangement is different, but, they need funding to support their treatment process. Another big one would be for capacity assessment. I just got off a call on this exact thing here earlier. This is where there's some sort of economic development in this kind of pretend town here, and it could be a factory, it could be a big residential area, so forth. Users of water and producers of wastewater, right? So that wastewater flow needs to eventually make its way to a wastewater treatment plant, kind of shown down in the bottom right. So, point A to point B, this network of piping, needs to be able to handle this additional flow. So, some very detailed information can provide, and somebody can make a judgment call and say, hey, these pipes can handle the additional flow from the factory or residential area that's being proposed. Another biggie, this is an advanced and a complex topic here, but it's hydraulic model work. So within the consulting engineering community, there are sometimes people that specialize in this, right? So, we do not offer this at Duke's, just to be clear, but quite often the service providers like us are working to support the engineering community that does this hydraulic model work. But kind of simply put, I mean, hydraulic modeling could be a whole seminar, but just in one page here, it's kind of a GIS-like digital twin of an entire wastewater network, or portion of the network sometime, and it incorporates the physical characteristics like pipe ID, the distances from one manhole to the next, slopes, elevation data, and ultimately it's used to calculate and predict level, flow, overall conveyance capacity of a pipe in situations like the capacity assessment. So, so it's a predictor of the characteristics of kind of what's going on in terms of level, flow, and velocity and so forth. However, that third bullet point, real life flow data is quite often needed to calibrate this model. It's not a laboratory setting out in the sanitary world, right? So some real life data is needed to kind of revise and edit and quote calibrate the model, right? So it obviously is an excellent tool for kind of long-term infrastructure planning for any utility. So getting into the meters and how they work, I mean, on a basic level, a section of gravity collection, sanitary sewer, it's a pipe that's on some sort of slope, hopefully, right? Percent slope equals rise over run. A common slope would be 2% or something like that, right? Or, a 200-foot segment might fall a couple feet from one manhole to the next. And then some terminology down here. Open channel, area velocity, traditional, gravity, flow monitoring, those are all the same, and that's what we're talking about, right? So we're talking about pipes that have a little bit of slope and the gravity makes it flow. There's no, there are pump stations out in the system, but for what we're speaking about and the topic today, we're talking about the gravity portion of a wastewater system. So getting into how the equipment works, there are two measurements that are critical. One is measuring the depth of the flow, right? So you can see how that's shown. And then secondly, measuring the velocity. These are two independent measurements. And with those, the flow value is calculated. And then ultimately, that data gets transmitted. So you see kind of, this is a piece of equipment. We at Duke's own some of this particular brand. There's several, predominant brands in the marketplace. And, some of them are better in different areas, but, it's a little bit of a Ford, Chevy kind of scenario. So, the equipment has been in the marketplace for, 25, 30 years now. So it's a pretty mature world and they all work well these days. So just to touch on the math part of it. So the fundamental equation is flow equals area times velocity. So I tried to kind of shade this cross-sectional area, right? So it's that kind of half circle shape. So that would be the real equation is very big and complex and so forth, but it's, the pipe inside diameter times a bunch of numbers, but it's ultimately how dependent upon how the percent full, right? It would be in units in square inches or some type of area unit. Velocity is just that. It's the speed, how fast it's moving. So, if the velocity equals 0, then the flow rate also equals 0, right? It's just a stagnant pond, but quite often that's measured in feet per second or FPS. And I don't know why Q was selected for flow rate, but it was at some point. So Q is the flow rate, and that's ultimately, if you do the math here, you'd be in like cubic inches per second or ultimately volume per time, right? And all that stuff gets transmitted to here to a web browser, right? All the newest platforms of any brand, there's a web portal of some kind, and it's possible to get the data in real time, right? So you can virtually real time. So you see the data, you can look at it, observe, set alarms. When the service providing community does this, when we do this, we're watching this data every day. We're setting alarms for ourselves in case of the data could potentially fail and zeros could show up. So we want to know when that happens so we can work to fix that. And that's just kind of a snip of what the data can look like, and we'll get into that in more detail here. So that's an example of some of the hardware you saw. That's called a logger, and this diagram on the right, that's kind of how it's set up, right? So the logger is somewhere up in the top part of the manhole. Quite often, it's attached to the ladder. There's different that it gets fixed somewhere in the top part of the manhole structure. And then that little blue sensor is referred to as a submerged type sensor. So it's a submerged area velocity sensor, right? And it's fixed on this flexible metal band that, the operator, when they install, they compress it, slide it up in, and it's programmed and so forth. But that's what it looks like. And in real life, this is a real life application, a picture. And ideally, it's very rare that these are placed on a 90-degree bend, but sometimes it has to happen. Ideally, it's a nice, perfectly straight through flow with no drops and an ideal velocity and an ideal depth and so forth. But that's what it looks like. So you have the sensor cable up there that ultimately makes its way to the logger. And if you look very closely where the bottom, the smaller red arrow, let me see if I can get my cursor going in here, you can see the metal band. And if you can see the blue sensor down there. So that's the blue area velocity sensor. All right, there's another type of sensor. These are referred to as non-contact sensors. One example of that is called a FlowDAR. There are several brands of this, but like this sensor, it performs the same measurement, but it looks very different, and it's the arrangement physically is very different. But this particular one is called a FlowDAR. It's been on the market for 20 plus years. There's bunches of them out there, but it's a different type of area velocity sensor. The basic advantage is it's not as prone to collecting debris. The sensor before that, the blue one, you can get sediment debris on it and it stops measuring ultimately. And here's kind of a cross-sectional drawing of that same FlowDAR non-contact sensor. You can see the ultrasonic depth measurement happening and then the velocity piece there. And this is what it looks like in real life, right? This is a typical application, road cones for safety and so forth, a tripod, gas monitors. It's a busy scene, right? There's a blower here to blow fresh air in to deal with the gases and so forth. There's a generator, there's fuel, all the parts and pieces. You can see the two loggers here. I mean, these are expensive setups. They're each setup, just rough terms, $10,000 each. And you can see he's using one as a laptop holder there, and there's a laptop and software and programming, and so some expertise is required. Meanwhile, the other guy's over here in the manhole, performing the sensor installation and making sure the cable is out of the way. And ultimately, it will look like this, right? So equipment's in the ground, can't see it. There's several different antenna types, but this is a cellular antenna. This is kind of a hockey puck style, and it just sits on top of the manhole and transmits data. Ultimately, to a cell tower, and typically these setups are set up to grab data in 5-minute increments is quasi industry standard. It used to be 15 years ago. 5-minute is very common now. And then, all of this is programmable, but it's very common to push the data to the server so it can be seen every 3 hours. It could push it every 5 minutes. It could push it every 24 hours. Um, it's just a matter of like how quickly are the batteries going to last. All right. So a normal project kind of timeline, so to speak, kind of start to finish for a study would be, some sort of, common, for all projects, some kind of kickoff meeting, right? In this case, it's determining, reviewing the target locations, the applications, traffic control requirements, so forth, and whether or not you got to get in somebody's backyard, notices, and all that stuff. Then the installation will take place. But getting into the data number three here, roughly 2 or 3 weeks after the equipment is installed, we typically like to strike up a meeting with whoever's on the receiving end and just kind of run through it. Hey, here's what it looks like. Can you get online if you want to even get online? If you want any alarms and so forth, but just kind of a quick check through the data, making sure that everybody is okay. From there, there's an ongoing review of the data just from a data quality perspective, maintenance as required. Typically, it doesn't go beyond 1 month increments, right? So, it's normally a couple of weeks to a month, but it's as needed. And generally that maintenance trip in a lot of cases is it's a basic level check. And really all that is somebody doing confined space, measuring the level. If it says 3 inches, back in the office, that guy should be seeing data that says 3 inches deep, right? And then if any corrections need to be made, that's when it happens. So at some point near the end of the project here, number six, there's kind of a pre-removal in quotations meeting with the client to just kind of run through, hey, is the data there that's needed? That's kind of when, if an extension is necessary, that's when that's discussed and kind of work through all that and just kind of tidy up the project. And then finally, whenever it ends, the hardware gets removed. Okay, so what about rain data? There's really two sources of rain data. This kind of bucket, kind of cylinder shaped object over here is a mechanical. It's called a tipping bucket rain gauge, and the tipping bucket is this seat. It's kind of a seesaw mechanism where there's a funnel. It fills up this part and it spills it, and then the other side fills up and it spills it the other way. But ultimately, there's an electronic sensor that's counting those, and it adds it up, and that's how there's a calculation done as to how much rain has fallen. So that's kind of the tried and true. We still use these sometimes, but in the industry, there's these specialty services that have cropped up that provide really high quality rain data, and just what we do, we use both, right? So quite often we're using the web service, and then sometimes we'll use the tipping bucket rain gauges. So some limitations and challenges in the flow metering world would be, I mean, obviously this picture over here on the left, when you think of the picture on the right, getting all of that hardware out into a swampy area, climbing up 10 feet, that's a tall order, right? Probably a no-go. It could be done if it's really needed to. I mean, I've personally been a part of one where we had to rent an off-road cherry picker, specialty piece of equipment and drive out really far and have a safe platform for the tripod, a winching mechanism, and just a work platform. So, that's certainly a challenge. This top picture, you see the road there. This manhole, very, very different than being out in the fast lane in a 4-lane, urban environment. So those are some really basic limitations. And then getting into the applications, very low level, low velocity. Look, the hardware that's in the marketplace, it can't measure a trickle, right? Moving at 0.0001 feet per second, right? No different than a car. You can't set it. It's not built to set the cruise control on 0.08 miles per hour, right? There's a sweet spot, and generally the lowest level that is practical for the current generation of hardware is about 1 inch. It can go less sometimes, but kind of inch is a good round number. And low velocity, kind of a half a foot per second. When it gets down to very, very slow, it just loses accuracy in terms of percentage. And then on the high flow side, like high level, high velocity, I've been a part of one where I think it was a 72-inch pipe. It was maybe 36 inches deep and moving at probably 4 feet per second. So there's an obvious safety element where you have a human being down in a pipe, right? Trying to install hardware, 72-inch pipe, and you know, it's a lot of safety procedures going into that. So that's part of a limitation. Yeah, the next topic we'll hit on here is, utility owned versus a service provider. And this is just, I mean, I'm obviously with a service provider, and I've in previous, earlier in my career, I've been part of like selling hardware, this particular hardware, in fact. So, I've been a part of this and seen it. But just general statement here. There are some utilities that can own and manage and run flow meter, have a flow monitoring program in-house, but I would say they are there's very few of them, and it's not common, right? So I can think of some that I know, but generally speaking, it just requires too much specialty experience and so forth. You know, turnkey, it's up and running in a few weeks. So we'll just kind of look at some bullet points on this. So, you know, it trying to do this in house, again, it's not to say that it's impossible, but it's very challenging. There's research time. There's heavy capital cost. Again, the hardware sets, just the base setup could be $10 and $15,000 per setup, right? That equipment fails very often. Sometimes it's troubleshooting. There's spares that are needed. Staff training and turnover, a big topic in our industry these days. A lot of confined space entry, so a lot of safety considerations, and then learning and understanding about specific applications. Right, so experience pays dividends here in the field. The field guy is, the field team is critical. The equipment, traffic control, programming expertise for sure. And then in the office, watching data and being like aware of what's going on. And then ultimately, what data is needed, right? So big difference between getting an Excel file with 10,000 rows of data and a summary report that says, hey, we put in 20 flow meters, and over here has an extra million gallons, and over everywhere else there's none, right? There's a big step between those two. And kind of my homemade analogy here would be kind of, having a driveway built, right? Service provider, you describe kind of the goals, and you jump right over here to a pretty driveway with flowers and so forth, hopefully, right? A lot of work in between, right? Could you get gravel delivered and have a shovel and a team? Of course, but it's a heavy lift. So when you start thinking about strategy of applying flow meters, this is a very basic example where those two yellow lines have, bigger systems. The bottom one is kind of off the screen there to the left, but the point is like two kind of sub basin systems converge and meet down there in the bottom right. So in this particular application, the utility had no idea which one it was coming from and needed to kind of understand which one it's coming from and by how much and so forth. So this one was interesting in that, one of them basically generated, the bottom one, no impacts whatsoever during a rain event, right? And the rain event is kind of in the time frame. These are the same time frames, top and bottom, but this spike up here is obviously during the rain event. So, the top area, massive difference and massive reaction and a very quick reaction, right, to the rain event. So you can see the flow rate here is probably 70, 80 gallons per minute on average. This is in units of gallons per minute, and climbed up to over 1,000, right? So we'll just kind of look a little bit deeper into kind of what the data looks like. So, quite often when we're pulling up data, we pull up these three channels. We pull up the velocity as an independent channel, and this one it's the purple color. We certainly pull up the level, that's the green color, and then the calculated flow result, right? The product is in blue, right? So you have, it's a busy graph over there on the left, kind of the vertical piece. The blue is in gallons per minute. The purple is in feet per second, right? That's the speed, and then the level here. So some quick observations. I didn't put the rain on the graph because it's too much data at one time, but an obvious rain event here, kind of in the middle here, this middle section. And so kind of the basis of the analysis would be like observing dry weather patterns so that you can see where that's shown, and then kind of the wet weather spikes and getting your arms around the volumes and the peak values and all that sort of a thing that we'll look at here. So for this one, I just took that same graph and stretched it out a little bit. So, this is a key parameter, this ADWF, or average dry weather flow rate. So in this one, the 3 days was averaged to be about 67 gallons per minute. That for the whole data span, that was kind of the solid baseline dry weather flow rate, right? So you look at that, and then you're like, wait a minute, what happened over here during this wet weather event? The peak flow rate, the instantaneous flow rate, barely topped 1,600 gallons per minute, right? So that's, in terms of instantaneous values, that's a peaking factor, what's called a peaking factor of, over 20 or about 24, right? So there's a big difference of an instantaneous flow rate versus a volume. And I often use the analogy of like, it's like turning on a garden hose completely open. It's coming out very hard, but you could turn it on and then turn it right back off. Big peaking factor, right? Going from nothing to a lot back to nothing, but not much volume. Like you're not going to fill up much of a 5 gallon bucket if you just turn it on, turn it off. So two different kind of concepts here, right? So you have the instantaneous piece of it, which is shown, and then you start getting into volumes that can be calculated in different time pieces, right? So, daily obviously would be one, right? So this one, for this example here, a daily volume of 96,000 gallons here, shown over here on the left. And then over on the right, 1.5 million gallons, right? So a big, big difference. And then you start thinking about like, hey, what's the total event, this whole rain event? What's the additional volume? In this case, 5.1 million gallons. So this one is pretty extreme, pretty extreme example here. But that's a lot of stress on downstream pump stations, lift stations, and wastewater treatment plants. And just something to consider here would be should sites be monitored just one time for a study period or longer term, right? I mean, the economics of it, longer term, the per month rate can come way down, right? But a study, a 3 month study is just a quick snapshot. So a couple slides here and we'll wrap up. But where area velocity fits into our world here at Dukes, I mean, the Dukes name first off is centered around what's called chemical root control, which is a root control process it's a turnkey service that's for mitigating roots out in a sanitary collection system. So you see we have the monitoring. We provide lots of SSES kind of services, TV and smoke testing and so forth. And then we develop like long-term programs. I've got an example I'll show you quickly. And then, we do things like hydro excavation, and in the western part of the U.S., trenchless sectional lining. So our portfolio of monitoring, number two is what we're talking about here, area velocity flow monitoring. We've got another service that kind of overlaps into that world a little bit called micro detection. Now, micro detection is just level only. There's no velocity measurement. So it's a fraction of the cost. The data is more limited, but can be very telling. Then we have 3 and 4, an alert, kind of a basic alerting service where that's turnkey. And then we get into providing lift station or pump station data, long-term solutions and short-term. So it's a pretty comprehensive setup, and quite often for studies, all of those make up a sanitary collection system, right? So quite often having area velocity data is only part of the equation. You know, having if there are downstream pump stations, that's the heart of the collection system. There may be SCADA, maybe not. Maybe the data is great. Maybe it's no data collection at all and just an instrument. So there, all of this stuff is tied together. Is the point that I'm trying to make here. All right, so I've got an example that I'll wheel through quickly, and then we'll wrap up with questions here. So this is a study that we've got queued up here. It's 1 million foot. There are 30 flow monitors. So as is often, this all of these studies are ultimately limited by the budget, right? There's an available budget of some kind, right? And otherwise you'd put a flow meter in every single manhole, right? But that's not possible. So you strategize and put these out as efficiently as possible. In this case, all of these purple stars represent a flow metering site, and they're placed in order to like isolate certain areas, right? This particular study is augmented by these micro detection monitors that are level only, so much less cost, right? But when you start diving down and looking at these smaller areas, you can see here, we've got one flow monitor in this example where we're getting, you know, exact flow, measured flow values, right? And then we have the level only, inflow and infiltration typically, and that's the basis of this project or reasoning, it's typically not evenly distributed. But this is a strategy. We've done them before where we're combining in pump station data, and but it's a just an example of kind of some strategies here that hopefully provoke a little bit of thought. But look, at the end of the day, at the end of an I&I study, usually you find some areas that impact the system, like we did in the previous example, and some don't, right? Now what? That's not the end of the road there. The utility has to do something about it, right? So, quite often we're building out projects like multi-phase projects where typically there'll be at some point some element of CCTV, right? Not every time, but sometimes, and then part of the thought process of doing the I&I study is to limit the TV and to really you focus it in and be strategic about it. And it may include smoke testing. Those are other SSES services, and sometimes we do webinars on those too. So, but this is just an example of a multi-phased approach. So I think I got pretty close to 30 minutes, but I want to thank everybody for jumping on. And again, that's my email address and phone number. Please feel free to reach out. And I think Caitlin will open it up for questions. I don't know if you have any typed in and so forth, but I'll let you go.
We do have a couple of questions that come in while you were speaking. But if anyone has any other questions before I kind of get to some of these, please just raise your hand and I will unmute you, or you can type it in the Q&A box at the bottom of the screen. The first question, Mike, that we got was, how much does this normally cost?
Yeah, so that's a very loaded question. The main factors are the number of sites. So there are projects, I showed you that one example that only had two, right? There are projects in bigger cities that may have 500, right? The unit price for each of those is very different. But I'll throw this out for a project that has, let's say, 10 flow sites, and it's a project that's 3 or 6 months. It could be a number that's between $2,000 and $3,000 per site per month. And that's not to say that's a quote, but just to kind of give a feel for that. It's application dependent, but we do a lot of work where the unit rate per site per month is in that between those two numbers. There's lots that are under, there's some that are over.
The next question was, how many meters does a utility need?
Yeah. So again, that could be, a lot of utilities have none, right? So you know, from my position, if I were managing a utility, I'd probably, it's would be wise to know and understand as best you can what's going on. So, probably a couple at each little main sub basin. Maybe there's usually flow measurement at the plant, and then depending on the nature of the problem, if it's an I and or we're really trying to pinpoint something, then you kind of can concentrate and do short-term studies. But a lot of medium-sized towns will have projects that are, in between 10 and 30 units is it's common.
Okay. And then the last question that I have right now, or actually I have two more, three more. How does backwater affect the readings?
Yeah, so good question, and I didn't address it, but that's a good one. So, yeah, so the area velocity equipment is built to be able to manage surcharge, meaning the system can fill all the way up. The pipe is full, water could go up, it could be an overflow, right? It's only measuring the portion that is in the pipe, and when it's calculating, it's going full pipe. So that crawl we learned about that area times velocity. It's using the area of the pipe, and however fast it's going, that is the flow rate. But the hardware, including the logger, could theoretically live its life underwater, but the reality is it's not going to. If it's surcharged and the equipment's going underwater constantly, it's trouble. We know all too well, but it's designed to do it.
Okay. The next question was typically how many linear feet of pipe need to be upstream of a monitoring setup?
Yeah, so the answer to that would be it's depending on what the goal is, but like I said, the equipment performs best in a nice straight laminar, even non-turbulent kind of environment. So whatever it takes to make that happen is the real answer. But I would say, typically when we're looking at applications, we want at least one segment, one nice segment and not an elbow coming straight in, right? Or not a convergence of like, a bunch of different sites where it could create turbulence. So I would say if you have one segment, typically these go in the influence side in the manhole. It's more times than not, it's an application to be considered.
Okay. Someone else had asked if we have or offer a product for I&I that is comparable to the FCS spill sense unit.
The what now?
FCS spill sense unit, if we have something comparable to that.
Yeah, I don't know what that's referring to. So whoever asked that, maybe put in the chat your email and I'll look it up and can send you a quick email about it.
Okay. And then one more question just came in, which was when would you want to use level only instead of flow monitoring?
Yeah, so level only typically is answering the question of, hey, I want to know where the impacts of I&I are, the location, and I want an estimate of the volume, right? It's less exact. And quite often in an I&I, finding I&I situation, if that I&I is producing 1 million gallons or 2 million gallons, it's still the same problem. Like go fix it, right? So level only can be a great tool in that scenario. We've done many hundreds of level only projects, but you certainly couldn't use level only for a billing application from utility A to B, and if the bill was $1 million per month, you would want a very comprehensive flow setup. So I think just the general answer would be just for locating I&I, level only can often be sufficient. But when exact data is needed for billing, hydraulic model type data, certainly a flow meter would be required.
Okay. All right. Does anyone else have any questions before we wrap everything up? All right. Well,
That
good.
it? Well, thank
Mike.
you.
That's it.
Yeah, thank you for joining. Appreciate it. Everybody
Thank
have a
you,
good day.
everyone. Have a great day.
Bye.